Hello, I'm Lloyd. Welcome to Starting Out with Quantum Computing. And in this podcast episode today, we have a very exciting topic. It is none other than the 2025 Nobel Prize for Quantum Computing. So let's just go straight into it. It's very momentous. On the 7th of October, so just a couple weeks ago, or actually a week ago from the time of this recording, the Royal Swedish Academy of Sciences announced a three-way Nobel Prize share for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electrical circuit. So that's quite the mouthful, but that is the official name for the Nobel Prize. And so we are going to dive into it a little bit. So they were sat around the tables at the Royal Academy's press conference, and we had three professors on the table. And we had, in the middle, we had the Professor Hans Allegren, who is the Secretary General, and he announced that the three scientists responsible for revolutionizing the field of quantum mechanics and quantum systems were John Clark, Michael H. Devoret, and John M. Martinis. And their work is honestly, it's incredible because it happened over 40 years ago, but they were able to, they're responsible for some of the breakthroughs that we see today in quantum computing. So let's talk a little bit about who they are. So John Clark, of University of California. He was born in Cambridge on the 10th of February, 1942. So John is an English physicist who has mainly worked on superconductivity, superconductors, and Josephson junctions. And his research has led to many advancements in the field of SQUIDs, which is the acronym for superconducting quantum interference devices. And his higher education started at the University of Cambridge, where he earned his bachelor's degree, as well as his master's degree and his doctoral degree as well. He then became a professor of physics at the University of California and a senior scientist at the Lawrence Berkeley National Laboratory. Now let's go on to Michel H. Devoret, of Yale University. So he was born in Paris in 1953. Michel is well known for his research in a field known as circuit quantum electrodynamics, or QED. He earned his engineering degree in 1975 from École Nationale Supérieure des Télécommunications, which is a very well-known university in Paris. And then he earned his master's degree in 1976 in quantum optics. And then he would finally complete his PhD in physics in 1982 from the University of Orsay. Then Devoret traveled to the US to join Clark's laboratory as a postdoctoral researcher. After completing lots of notable research, which was one of them, of course, was Nobel Prize worthy, he then moved on to other endeavors, and today he is the chief scientist at Google Quantum AI. Then finally, we have John M. Martinis, also of University of California. He's an American physicist born in 1958, and he is known for pioneering work in quantum computing, especially at a time, take the 1980s, in which everything was mostly theoretical. Martinis got his bachelor's degree and doctorate in physics from the University of California in 1980 and 1987, respectively. He met Devoret during his doctoral studies within Clark's laboratory. Martinis would go on to complete postdoctoral fellowships in France at the Alternative Energies and Atomic Energy Commission after his research. And since 2020, he moved to Australia to join the quantum computing startup Silicon Quantum Computing. He then co-founded a company known as Colab, a company which is trying to improve the coherence of superconducting qubits. And you do see a lot about them, or at least I do, online, through LinkedIn, etc. So let's talk about the actual Nobel Prize discovery. So quantum tunneling generally doesn't exist in our large-scale world. For example, even if I hit a tennis ball at a wall, we know that it will never pass through this wall, unless I'm perhaps Carlos Alcaraz. However, at the smallest of scales, in the microscopic regime, the quantum mechanical phenomena known as quantum tunneling can actually occur with high probability. The Nobel Prize this year recognizes that the 3 scientists were able to observe this tiny phenomena on a macroscopic scale back in 1984 to 85. How did they do it? So they started with an electrical circuit. They cooled it down until it exhibited superconducting properties, such as electrical current with no resistance. They then separated the circuit into 2 partitions with a thin layer of material with 0 electrical conductivity in between. Now, in theory, this should mean that the circuit will have no current flowing throughout it, as it should be stopped by the partition. However, the team were able to effectively show that they could still control the current, meaning that the charged particles making up the circuit must have been tunneling between the partition. But what makes it macroscopic tunneling? Because we already know that quantum tunneling exists. We've already, scientists before this had already experienced the idea of microscopic quantum tunneling. So what makes it macroscopic? You see, in an ordinary circuit, current can flow because of free-moving electrons. However, within a superconductor, current can flow because of the formation of Cooper pairs. These are pairs of electrons that get stuck together at cold temperatures. Unlike electrons which repel each other and can be distinctly identified, therefore, Cooper pairs are not so sensitive to each other. And this means that Cooper pairs in a superconductor can basically be described as one large combined system, a quantum mechanical system. Moreover, the Cooper pairs behave as though they were an entire large particle that fills the entire circuit. So, in order to identify macroscopic tunneling, the team would need to create a superconducting circuit with a barrier and measure a non-zero voltage. And this is exactly what they did. They showed that the tunneling voltages could be measured and even that they were quantized, meaning that the voltages could only exist at certain values. So remember, quantized means, much like the analogy of rungs on a ladder, you can only have certain levels, at certain heights or certain energy values. That's not continuous, it's discrete. And this proved that the Cooper pairs were acting like a single giant particle and showed that quantum effects were not just reserved for the microscopic regime in the microscopic world, but in fact could cause effects in the macroscopic world too. So what does this experiment tell us? What does it offer for us? What are some of the physical realizations of this experiment? Firstly, as a passionate physicist myself, I must say that the results of this experiment greatly develop the field and the theory of quantum mechanics. Experiments that benefit theory are equally as important as theories that benefit experiment. Generally, experiments that have measured macroscopic quantum effects have been composed of tiny separate effects that have been added together. However, this case is fundamentally different. This is truly one whole macroscopic quantum system with a measurable voltage. This can have many theoretical implications. For example, Schrödinger's cat is generally said to be in a superposition of dead and alive until being measured by the large-scale environment, such as a large observer. Schrödinger believed, therefore, that the quantum properties of a system were erased at the macroscopic scale, which is generally true, and that, in other words, the cat can't be quantum at large scales. However, in contrast, this new experiment begs to differ slightly, demonstrating that, albeit still very small, Cooper pairs, macroscopic quantum phenomena can exist and can generate large observable quantities, such as a change distinctly measuring voltage, non-zero voltage. So this is exciting. This research has already been of benefit for so many intersecting areas of quantum. For example, the manufacturing of artificial atoms builds upon this previous research and can be used to develop new forms of quantum technology. Furthermore, the energy quantization that was demonstrated by these 3 laureates can be used to make a quantum bit or a qubit, and has actually been used to make a quantum computer. The fundamental building blocks of this quantum computer are qubits. So therefore, this research subsequently boosted the field of superconducting quantum computing. Therefore, this year's Nobel Prize laureates have both contributed to the theoretical field of quantum physics as well as the practical side. Thank you very much for listening to this week's podcast. My name's Lloyd, and I hope that I see you next week for another entertaining podcast. All right, thank you very much.